All right, in this video, I'm actually going to cover one more topic from chapter 4, which is supplemental to the core objectives of this course. We teach it, but I learned about this when I took this course several years ago. I don't think it's an extremely difficult concept, and I want you to understand this because it kind of sets us up for some additional topics later in chapter 6, I believe it is. So let's go ahead and let's talk about Cauchy-Euler equations. And the Cauchy-Euler differential equation is going to be one in which I have the x to the n multiplied by the nth order derivative like this. Dot plus a1x dy dx plus a0y is equal to, and it can be g of x over here, but in all of our examples, it's going to be 0. And we can transform this into a model that's very similar to what we did earlier in chapter 4 with a substitution. We're going to let y be equal to x to the m. And then we're going to find our derivatives. Y prime equals mx to the m minus 1. Y double prime equals m times m minus 1. X to the m minus 2. Y triple prime equals m times m minus 1 times m minus 2 times x to the m minus 3. I think the highest we're going to go in our examples today is the fourth derivative. So that would be m times m minus 1 times m minus 2 times m minus 3, x to the m minus 4. We're not interested in the trivial solution to these equations where x is 0. If we have it homogeneous, we're not interested in the fact that 0 to any power is going to be 0. And if I have x0, y0, those types of solutions, I'm not really interested in those trivial solutions here. So I'm going to be looking for solutions that are, I'll show you, it's just like before, where there's 3 cases, where there's either distinct answers, or there's repeated answers, or there's complex answers. So distinct real answers, repeated real answers, or usually the third case we're looking at is distinct complex answers. So you can extend case 2 into case 3 and figure out what to do with repeated complex answers as well. These are very straightforward, so I'm going to do a lot of problems here in a short amount of time. So this is going to be x squared, y double prime, minus 2y equals 0. And we see that we match here that this is second degree, second order, 0th degree, 0 order here. Let y equal x to the m. Y prime equals m, x to the m minus 1, and y double prime is equal to m times m minus 1, x to the m minus 2, make that substitution, x squared times m minus 1, x to the m minus 2 minus 2x to the m equals 0. And pull the, m times m minus 1 rule of exponents. When I multiply like bases, I add the exponents. going to factor out the x to the m that's common and just look at m squared minus m minus 2. That's what's left. And again, I'm not interested in this piece. That's trivial. M squared minus m minus 2 equals 0 is what I'm interested in. So I'm going to factor that. M minus 2 times m plus 1 equals 0, m equals 2, or m equals -1. And so we're going to have the form of c1x to the m now because of this substitution that we were looking at here, that we found our m's. So y is going to be linear combinations of x to the m here, like that. All right. Next one is is xy double prime plus y prime equals 0. I can multiply through by an x without changing anything to make this Cauchy-Euler. So I don't want x to be 0 in this, so that's great. Now we have x squared times, and y double prime is m times m minus 1, x to the m minus 2 plus x times m times x to the m minus 1 equals 0. So this is m squared minus m plus m x to the m equals 0. I'm only interested in m squared minus m plus m equals 0. So this is m squared equals 0. M equals 0, multiplicity 2. To see what happens with the repeated root here, y equals c1 x to the 0 is 1. So that's just a constant plus c2. And then normally we would have had x, times something. But if I want to now have a repeated root, I'm going to have ln of x. And that goes back to the fact we've done an exponential function, and so the way to get x is with x is equal to x to the anyways, it's you can look and you can see that the instead of multiplying by x, you're going to multiply by powers of ln of x. That derivation is in your book. So that's what's different about Cauchy-Euler. It's one of the things that's different about them. Let's keep going here. X squared y double prime plus x y prime plus 4y equals 0. So this is m times m minus 1 plus m plus 4x to the m equals 0. M squared minus m plus 4 equals 0. M squared plus 4 equals 0. M squared equals -4. M equals plus or minus 2i. We have a 0. So our form for complex is going to be x to the when we have m equals alpha plus or minus beta I, we have the form x to the alpha c1 cosine of beta ln x plus c2 sine of beta ln x. So okay, just remember ln x stands in the place of x like you were used to. So y equals x to the 0 is 1. So c1 cosine of 2 ln of x plus c2 sine of 2 ln of x. Moving right along to number 7. X squared y double prime minus 3xy prime minus 2y equals 0. So I have m times m minus 1 minus 3m minus 2 equals 0. M squared minus m minus 3m minus 2 equals 0. M squared minus 4m minus 2 equals 0. That can't be factored across the rationals. So plus 4, m minus 2 squared equals 6. M minus 2 equals plus or minus root 6. M equals 2 plus or minus root 6. So y equals c1 x to the 2 minus root 6 plus c2 x to the 2 plus root 6. It's a real number. It doesn't matter that it's not a rational number. It still fits case 1. Number 9, we have 25x squared y double prime plus 25x y prime plus y equals 0. So we have 25 times m minus 1 plus 25m plus 1 equals 0. 25m squared minus 25m plus 25m plus 1 equals 0. 25m squared plus 1 equals 0. 25m squared equals negative 1. M squared equals negative 1 over 25. M equals plus or minus 1/5 I. There's a 0 there. So y equals x to the 0, c1 cosine of 1/5 ln of x plus c2 sine of 1/5 ln of x. Number 11, x squared y double prime plus 5x y prime plus 4y equals 0. So this is m times m minus 1 plus 5m plus 4 equals 0. M squared minus m plus 5m plus 4 is 0. M squared plus 4m plus 4 is 0. And m plus 2 squared equals 0. So m equals negative 2. Multiplicity 2. Y equals c1 c1 x to the negative 2 plus c2 x to the negative 2 ln of x. Moving right along to number 13. Three x squared y double prime plus 6xy prime plus y equals 0. So this is 3 times m times m minus 1 plus 6m plus 1 equals 0. 3m squared minus 3m plus 6m plus 1 is 0. 3m squared plus 3m plus 1 is equal to 0. This is going to be the same thing as m squared plus m plus 1/3 is equal to 0. So m squared plus m equal to negative 1/3. Half of the middle number squared is going to be 1/4. So m plus 1/2 quantity squared is equal to, make a common denominator here, negative 4/12 plus 3/12 is negative 1/12. M plus 1/2 is equal to plus or minus 1/2√3i. That's not rationalized yet, so that is plus or minus √3/6i. M equals negative 1/2 plus or minus √3/6i. So y equals x to the alpha times c1 cosine of beta ln of x plus c2 sine of beta ln of x, like so. And let's go ahead and do another one. 15 x cubed y triple prime minus 6y is equal to 0. So we have m times m minus 1 times m minus 2 minus 6 is equal to 0. So this is m times m squared minus 3m plus 2 minus 6 equals 0. M cubed minus 3m squared plus 2m minus 6 is 0. M squared times m minus 3 plus 2 times m minus 3 is equal to 0. M minus 3 times m squared plus 2 equals 0. M equals 3, or m squared plus 2 equals 0. M equals plus or minus √2i. Y equals c1x to the 3 plus, and that's 0, so c2 cosine of √2 ln of x plus c3 sine of √2 ln of x. I have one more that I want to do before we leave this chapter. It's number 17. So this is going to be x, y, 4 plus 6y triple prime equals 0. I'm going to multiply through by x to the 3rd. X not equal to 0, so x4, y4 plus 6x cubed, y triple prime equals 0. X not equal to 0. Then we're going to have m times m minus 1 times m minus 2 times m minus 3 plus 6 times m times m minus 1 times m minus 2 equals 0. Common factor here of m times m minus 1 times m minus 2, leaving me with m minus 3 plus 6 equals 0. M times m minus 1 times m minus 2 times m plus 3 equals 0. So y equals, get my zeros, m equals 0, or m equals 1, or m equals 2, or m equals -3. So y equals c1 plus c2 x to the first, c3x to the second, c4 x to the -3rd. And that'll be it. These are Cauchy-Euler differential equations. It'll kind of help to have seen this a little bit before we go into some of the stuff in chapter 6. But right now we're going to go into chapter 5 and look at some of the applications of linear differential equations with things like circuits, springs, and so on, both with undamped and damped motion, or undamped and damped circuits, and things like that. And it's going to work out with these 3 cases very much like this, which we've already done, same types of solutions that we've seen, and we'll talk about our steady state and so on, and we'll try and find our particular solution, and probably even do some examples of some initial value problems, because those are really important to figure out with those circuits and springs and so on. So, all right, see you next time for some examples from chapter 5.